Okay, so I had left you with a problem on Tuesday. Have any of you given it any thought? Did you see any connections with network flows? Okay, so that's a good thing, right? I mean, it is not very often that you are taught about something and then you're given some other problem and then like, I cannot see how these two things can even be related. But we will see that they are. But before we get into it, fortunately for you, the semester is coming to an end. Okay, we have, what is it, 1 week and some. So we have all of next week and then the Tuesday after next week, and that is it. So my plan is essentially to spend next week, or at least as much of it as is necessary, depending upon what your responses are, as much of it as is necessary to do NP hardness. And if we finish with that, then we will have another 2-hour lecture on Tuesday. I will cover maybe one small topic and then we will wrap up. Okay? Any questions so far? I realize that this course has been, to say the least, strenuous. And the reason being that we have one core algorithms course and we have to cover as many topics as possible so that you can all go and get that Google job that you're all looking for, right? Either with Google or with any of the other companies, nowadays it looks like you have to do an algorithms course because most of you will be quizzed on problems in algorithms. That said, don't convince yourself that you're either good or bad in this field if you do want to proceed with this field. The exams were all 1-hour exams and your final is going to be a 2-hour exam. It does not at all reflect whether you know the field or whether you're good at it. Some people are a little slow. It takes you a day to even understand the problem. If you spend a day understanding a problem, you're not going to do well in the exams. However, most of the algorithms problems that do remain are the kind of problems that you will spend 6 months, year, maybe more trying to crack. Okay? And that is completely different from this. So if you did well in the exams, it doesn't mean that you're really good at this field. You have to find out based on questions whether something gets triggered in your head. And sometimes the problems are beyond that. So you can try everything that is out there and then you realize that this problem is really novel and then you have to take that extra step to crack it. And that requires pure creativity. So here's a field that at its core is almost completely based on creativity, and therefore it is not like many other fields where you can take a little from here and a little from there, mix it all up, and suddenly you have something that you can sell. Okay? I have also posted, I got many emails about the final exam. As we know, this class is very large, so it is not up to us to decide when the exam is going to be held. This room is going to be provided to us during a very particular period of time. I think it is 3 o'clock to 5 o'clock on either the Monday or the Tuesday after the semester ends. But I've posted it on the web page. You can also verify it against the registrar's website, and essentially all you need to do is pick up the exam period from the table we have for courses and just plug it into the registrar website. It will tell you when the exam is to be held. It will be held here, but at a very different time. It's neither going to be in the morning nor at night. It's someplace in the evening. Some of you do well evening, some of you don't, but that's one other factor. Okay, so any questions? Yes. We are going to, so given that we have very short time left, in a standard course I would have given you one last assignment. Now what I'm going to do is I'm going to give you an assignment which will not be graded, so you can check and see the kind of problems that are going to be, that might come in the exam. But on top of that, I have to give you a survey paper. And I told you before, the survey paper has little to do with what I believe should be taught in this course. There is a requirement of a survey paper now that we have joined something called SSCS. And here's a company, I believe, that requires that the courses that it is going to check to accredit the university have to have a kind of a survey paper, and I am going to set out the survey paper by Monday. Okay, so I'll tell you exactly what you need to do. Yes. Repeat the question, I couldn't hear you. For dynamic programming, yes. So we will cover one more dynamic programming today, okay, and that will be it. So you can see the dynamic programming itself gets applied in various fields. There is a core concept underlying it, and today you will see another example of the application of dynamic programming. Any other questions? Okay. So let's get back to the question we were asking last time, which on the surface did not have anything to do with network flows. So the question was, okay, maximum bipartite matching. And what do we mean by that? Well, a bipartite graph G is any graph that can be partitioned into two sets such that you have a bunch of nodes here, a bunch of nodes here. Once again, this is a cut. And the claim is all edges go across the cut, by which we mean that there are no edges on this side, no edges on that side, and the only edges you can see are edges of that nature. Okay, so you have a bunch of nodes on this side, a bunch of nodes on that side, you have edges going across the cut. And in the case of bipartite matching, the question is one of, given a bunch of nodes here, let's say there are m nodes, and given a bunch of nodes here, let's say there are n nodes, and assuming that there are some connections of that nature, can you match some of these to some of those? And a maximum matching is, can you find us a maximum matching of this? By which we mean, can you find me the maximum set of nodes that can be matched on the other side? And when we say match, we simply mean that you are allowed to match somebody on this side to somebody on that side if you have an edge. Okay, so this person really dislikes that person, this person likes that person. So in some sense, we are maximizing the total likeness of this whole set of things. You can think of these as being males, females, setting them up for some ball. Okay, and there are various other situations in which we do this. In fact, this is a big problem even in airports. You tend to match planes to gates. Okay, there are a bunch of gates out there, a bunch of planes coming in, and at any point in time, it's certainly far more complicated than this problem, but that's also a matching problem. So there are many, many kinds of matching problems. One of a kind, another of some other kind. You want to find the maximum set that match from the left to the right. Okay? So let me, instead of just throwing you a bunch of theorems and telling you that it can be done, let me show you the intuition behind why it is that this one has something to do with network flows. In fact, a particular kind of network flows. Okay? So we will see that in the following sense. Let me take the smallest example possible. So here's an example, right? And if it turns out that I match this person to that person, see, you have things on the left, things on the right. If I match this person to that person, then very clearly that's the only match possible, because this then remains unmatched. This person would have liked to get matched with this, gotten matched with that, but since it's already matched here, this person doesn't get a match. And therefore, this particular match is not the maximal match. The maximal match would be the following. Okay? Now look at this and see whether it tells you something that sort of says, hey, I can see it might be related to network flows. This picture that I've drawn. You are seeing those squiggly lines as matchings. Can you see the squiggly lines as something else? Yeah. Forget making it complicated. No cuts, nothing. I'm just looking at the squiggly lines and I'm asking a much more basic question. Can you see the squiggly lines? Because remember, the other domain is one of a directed network with capacities on top of it with flows on top of those capacities. Okay, several layers of things out there. Here it looks nothing of that kind. So you have three things out there: a directed network, positive capacities, a flow on top. Here is just a graph, but what I'm saying is that I've drawn some squiggly lines to show you the matching, and I'm asking you, can these squiggly lines remind you of something that says, okay, maybe I can now connect these two problems? How about, well, I'll not add anything to the squiggly lines. It's not going to make a difference. Flow. If you start seeing the squiggly lines are as actually carrying some kind of flow, you have hit upon the right idea. This is where the whole story starts basically. Okay, so essentially what we are saying is that if I can look at this and say, okay, so what I am looking at here is there is no flow on this, there seems to be a flow on this. That is where we start by connecting the two problems, and now we have to set it up in such a manner that it has a clean connection. So what I'm going to do is, first of all, make it a directed graph. It does not matter at all because I can either go from this side, trying to match these guys to those guys and out, or those guys to this guys and out. And so having a directed graph from one side of the bipartite graph to the other side does not make a difference to the problem. So what I'm going to do is, first of all, I'm going to make those directed lines. Okay, step one. Step two is to look at these and say that when I have a squiggly, I want that squiggly to be fully representative of a flow on this path. In this scenario, what you are basically saying is you are assigning a tick mark to some lines and not assigning the same tick mark to other lines. Right? So it's a discrete problem, a 0-1 problem here that you are solving. U, and so on and so forth, and not U edges. So you're choosing a bunch of edges. We have to enforce that. So what I'm going to claim is that I'm going to say that it is a 0-1 problem, and therefore on the other side I want the capacities to be 1. And if there is a flow of 1, then it means I have ticked that line. If there is no flow of 1, I haven't ticked that line. So I'm going to first make the capacities 1. All capacities 1. Okay, so 2 for all C, U to V. The capacities are all going to be 1. Okay, so that's number 2. The next thing I realize is that this matching problem is saying that everybody here has to match one person, not more than one person. You cannot have both of them match that person. That turns out to be a very simple but clever thing we can do with capacity networks. What I'm going to say is that the only thing coming out of there is a 1. Okay, so for each person, I will give a capacity of 1 coming out. And likewise, I know that this person also has the capacity to only match somebody. So this side also I'm going to give a capacity of 1. Mind you, these are all directed edges. So I'm going to have a source S with a bunch of capacity 1 lines going out. Then these edges which were there from the bipartite graph, I assign them capacities of 1, and then exactly a capacity of 1 coming out on that side, and that's my sink. Now I'm going to claim that this is a network flow problem, and all I need to show you is 2 things. So matching implies integral flow, and integral flow implies matching. Mind you, I'm saying integral flow. So I can show you a simple example like in this one, where in spite of what I did, this was the original problem, right? So I had a simple network here. I put a source here, I put a sink here, I put capacities of 1 everywhere. And you can see that I can maximize this. So we know that the matching in this case is 2, meaning that this guy gets matched to that and that gets matched to that. But I can show you a flow which is non-integral that you can look at and say, I don't know what you're talking about. And it will be a maximum flow. So what I know is that it is 2, and therefore I am going to send a flow of 1 on this side, a flow of 1 on this side. Okay, this example is not working out, but essentially what happens is I can take a 1 and spend it as a 0.5 on one line and a 0.5 on the other line. Okay. I needed more nodes to do this. So essentially if I had another node coming in, I could send a 0.5 through there so that it can get a flow of 1 on the other side. But in this particular example, I can clearly see that I don't have enough nodes to play that game. Basically the game is to split up your flows so that they go and end up with a 1 on the other side and then go with a 1 outside. Okay, that is possible. And so what I'm trying to show you here is that a matching implies an integral flow, and an integral flow implies a matching. These are both trivial. Why is it that a matching implies an integral flow? A matching is one in which exactly 1 on the left side is matched to exactly 1 on the other side. Okay, it might not be a maximal matching. Some on the left will be matched to some on the right. If you put a flow of 1 through them, they can easily leave and go to the sink. And therefore, it is going to satisfy the capacity constraints. The other constraints are just about flows themselves. So the skew symmetry and the flow conservation all come naturally because of the way you define the flow. But essentially all I'm saying is that if you have a matching from group of nodes to a group of nodes, and by which I mean not a maximum matching, just a matching, then it simply says that this guy is matched to that and that is matched to that, and no person on the other side is matched to more than 1 on this side, and no person on this side is matched to more than 1 on the other side. And therefore, we have these lines we know on which we can send a flow of 1. So for a matching, I can give you a flow. Assume that you have an integral flow now. Okay, so this side, therefore, is trivial. If you give me a matching, I can turn it into an integral flow. Not a maximum flow, but a flow. The other side is if you have an integral flow, then I claim that you have a matching. Well, the great thing about having an integral flow on a capacity network where the capacity is 1 is that the flow is either 0 or a 1. Do you see that? If you have an integral flow, by which I mean that the flow has to be an integer, the capacity is essentially 1. So the only integers that you have less than 1, less than or equal to 1 is 1 or 0. So the flows will essentially only be 1s or 0s. So if you have a flow which is integral in this network, some of these lines will have a complete flow and some of them will not. Right? Some of them will hit the capacity with a 1 and some of them will not. Now look at those, just line them up. And because of the way we have set things up, we know that each one is either triggered by a flow or not triggered by a flow. For that I have a matching. I claim that that is matched, and then if that flow is coming in, it has to leave with by some route, and that route cannot be a 0.5 and a 0.5 because the flow is integral. And therefore, it is going to go down exactly one line, and that will be your match. If it goes down that line, we know that this guy does not get any other flow coming from any place else because of the constraint coming from the other side. So all of these put together say that if you have an integral flow in a capacity network where C is equal to 1, you are going to end up with a matching. So that takes care of that. That essentially means that every time I can produce an integral flow, it is a matching. We now know that Ford-Fulkerson is going to give you a max flow. And at the same time, Ford-Fulkerson, because of the manner in which it proceeds, is going to give you an integral flow. Remember, there are all these other kinds of flow algorithms that will not fit this. If you have a flow algorithm that sometimes sends out a 0.5 someplace, that is going to break this entire thing. The only reason we can apply Ford-Fulkerson is because Ford-Fulkerson does the following. It starts at 0, it finds an augmenting path, it finds a minimum on that augmenting path and gives a flow equal to that. And because we are starting with a flow of 0 and the augmenting paths have only integral capacities, the minimum is going to be an integral capacity, and therefore the first flow will be integral. On top of that, you will slap a second flow. Now we can clearly see that the residual network is again going to be integral, and therefore the second flow will be integral, and so on and so forth. So Ford Fulkerson, the way it approaches this problem, is always going to end you up with an integral flow. We also know that Ford Fulkerson, in spite of the fact that it is giving you an integral flow, I have proved to you last time that it gives you the max flow. So all of these little pieces put together tells you that if you ran Ford Fulkerson on this thing, it would give you a maximum bipartite matching. Okay, these are two very different concepts, but somehow they come together. And now instead of going around and scratching your head and saying, who will I match with whom, all you do is you put these pipes in, you put a source here, you put a sink here, and pump water. And it just tells you who will match with whom, the best possible match. Yes?
Why, when we find a path for Fulkerson algorithm, why if we use more than one crossing in the bipart? In principle, it's not going to happen because all the directions are from the left to the right. But when we start running for Fulkerson, we are going to change the angle.
Yes.
Eventually. What when we go back and take in one
When you
path?
go back and forth, you are killing. Okay, so here's a very nice thing. So you are asking, what is the implications of Ford Fulkerson actually sending flows in the opposite direction, right? Remember, when you have a residual network, even though the capacities look like this, when you have a flow in this side, the residual network tells you a negative flow on the other side, and maybe Ford Fulkerson is going to use one of those. What is really happening is that every time Ford Fulkerson pushes one unit of liquid, it is essentially saying that I came here, I don't like that matching. Okay, so I'm going to take this matching off, I'm going to match this guy with that guy. And I'll match that guy with somebody else. How does Ford Fulkerson take a matching off? It pushes a flow in the wrong direction to cut off the one. So there was a unit flow going one way. Ford Fulkerson has a capacity to pull out that unit flow. That essentially means that Ford Fulkerson is also going about in a very organized manner, taking out matches. It starts with a particular matching, few people, and then it says, I don't like this match, I'm going to remove this match. And that is how it sends, and the way it removes its match is going the opposite way, killing the flow. The only way stuff happens is that the flow either is 1 or suddenly becomes a 0. Because you are still doing integral. Does that answer your question? Sort of. So you have to think very carefully about situations where you can apply this particular way of thinking. This is just one problem where you apply Ford Fulkerson. There are many other kinds of matching problems where you have to very carefully apply Ford Fulkerson and argue to yourself that whatever Ford Fulkerson is doing is not messing up your problem. There are several of these problems in the book. You can go and check it out. And we are finally done with graphs after all these years. Okay? So I'm going to cover one last topic, and then we will get to NP hardness next time. And the topic is something that all of you should be familiar with, and therefore is being covered. "30 years back, this was just a theoretical problem. Some of them played with it and went away with it. And suddenly, with the arrival of bioinformatics, this has taken on huge proportions. Everybody wants to know what is the longest common subsequence. What is the problem, and why do we address it? So let me tell you what the problem is. For some strange reason, we have something called a DNA, which essentially is made out of 4 nucleotides. And for some other strange reason, we have found out that when we take our own DNA and compare it to that of a monkey, we find tremendous amount of similarity. That is not to say that I am telling you that we are related to monkeys. Okay. Some people believe we are from monkeys, some people don't. I do not care. What I can tell you is that given a sequence that is coming out of our bodies and a sequence that comes out of a monkey's body, strangely enough you see great similarities. And if you go from a monkey to a crocodile, you again see similarities. And from a crocodile to a cockroach, you see similarities. Some people believe that these similarities essentially mean something. Other people believe that it means nothing. For those who believe that it means something, they have created something called a tree of life, where they say that I can take you from one animal using its DNA sequence to another animal with shortest number of changes and so on and so forth until I change one of these sequences to one of those sequences. Okay? I am not going to take a position on this terrible issue that we have, and yet from a technical point of view it is very clear that you can actually take these sequences and see, hey, this sequence I find to be quite similar to this sequence and substantially different from the other sequence. For example, if you pulled out a DNA sequence from you, pulled one out from a friend of yours, you would find tremendous similarities. Almost 99.9% of this is the same. If you pulled it out from my friend a monkey, you would find tremendous amount of similarities, not as much as you would find with your friend. If you pulled it out from a cockroach, you would still find a lot of similarities, but not as much. And therefore, we can start asking these questions. If you just wanted to ask this question, which is that can I now create some kind of graph where the distance between two of these things is this notion of a distance between their DNA sequences. And some people will look at that and start making assumptions about how things happen. Other people will look elsewhere to think about how things happen. But the whole story is that if you believe that DNA sequences have something to do with the distance between you and some other animal, then you can set it up and get a real number for it. Okay, so that is the background. So the question now becomes, what is this number that you want to assign? I give you one sequence and I give you another sequence. So here's a sequence. Okay, I give you one sequence, and here is another sequence. I find that there is no reason for these sequences to be of the same size. But what we can say is that we assume that things in nature don't just squiggle around. So these are really sequences, DNA sequences. So we cannot take the whole thing and say it's a bag of A, C, T, and G. In fact, the only reason that DNAs can produce proteins is because it is in this sequence. It is a surprising thing that nature has figured out that in order to produce proteins, which has its own alphabet. So nucleotides have an alphabet of 4. Proteins have an alphabet of 20. Okay, so these are nucleotides. There is something else called amino acids, and this has a group of 20. And it is really strange that nature sometimes thinks as trivially as human beings do, which is that nature said that I want to code for 20, so what can I do? What is the smallest number of nucleotides I can use to code for 20? And it turns out, and you do the calculations, 2 is not enough, because 2 is 4 times 4, which is 16. So 3 is the smallest that you can use to code for an alphabet of 20. And lo and behold, nature has said that I'm going to look at triplets of 3s. Each one is a code for an amino acid. So here is a strange amino acid, another one, and so on and so forth. And so DNAs code for proteins. Groups of 3, groups of 3s, you essentially take out the appropriate amino acids, string them up, that becomes your protein, and protein catalyzes everything in your body. If I take your proteins out, you would stop. all the operations in your body are catalyzed by proteins. You put A and B next to each other, they are not going to have a chemical reaction. You put A and B and a particular protein next to each other, and immediately they will have the chemical reaction that you're looking for. It catalyzes the thing. How does it do it? Well, proteins squiggle up, whereas DNA has a very good structure. Proteins, when you string out these amino acids, they suddenly bundle up and produce some strange holes in them which have charges. And those holes are essentially used to do everything in your body. You are asking me, how do I know all of this stuff? Well, for a short period in time, I was also interested in this problem and therefore read all about it. Okay? But coming back to our problem, I give you this sequence, I give you that sequence, and I want some notion of a number. And the easiest notion of a number that you can come up with is this notion called edit distance. Because these are strings made out of alphabets, you can ask the following question. And the one we will address is even simpler than the one I can tell you. Give me the smallest number of deletions, insertions, and maybe changes that will turn this into that. Now, when I say deletions, insertions, and changes, it messes up the problem for you because a change can be seen as an insert and a delete. Okay? But it turns out that certain things have a higher propensity to change to other things than this is in reality. In reality, it may simply be that A going to a G is more probable than C going to a T. We are not going to look at that at all. So, to keep our problem simple, I will simply say, give me the smallest number of deletions and insertions that is going to change one sequence to the other. Why do we believe that this is a good way of looking at distances between animals? Well, we know that over time there are mutations. Sometimes you simply lose a nucleotide. Sometimes you suddenly gain a nucleotide. It turns out that you actually sometimes gain a whole sequence, something from some place, some bacteria suddenly inserts it into your DNA. That's a more general problem. But you can look at that, abstract it away mathematically, and end up with a problem where you are simply asking how many deletions and insertions on this one will allow me to get here. I then ask, what is the minimum number of deletions and insertions that will do this for me? Because I know that I can delete all of these and then just add all of those. But that is not the problem. The problem is, what minimal change can you make to this sequence to make it look like this sequence? Yes? This will become the long, yes. So, one way of looking at deletions and insertions here is to look at deletions and deletions on both sides. So, I give you two sequences and I say, what is the minimum number of guys you can delete from here and the minimum number of guys you can delete from here, so that what you are left with are the same. Can you see that it is the same thing as deleting and inserting here? When I delete things, I end up becoming something smaller than the other guy, and then I start inserting stuff here to make it up and become the other guy. That is equivalent to saying that I delete from here, make it smaller, delete from here also, make it smaller, so that they are the same. You see that? How many people do not see what I just said? How many people see what I just said? Okay, very good. So, my problem now is, what is the minimum number of things deleted from here and the minimum number of things deleted from here, such that the remaining sequences become the same. Another way of saying is that what is the longest common subsequence between these guys? If you give me the longest common subsequence, then I can look at that subsequence and remove the other guys. So, there will be a central little guy, it is the longest common subsequence, and you can essentially, if you want to go from here to the subsequence, you essentially have to delete some, and if you want to go from there, you delete some others, and they become this subsequence. So, the whole idea of the minimum number of deletions corresponds to the longest common subsequence. So, that is the problem that we are going to address. A subsequence is given a sequence, you take out some guys, that gives you a subsequence. Given another sequence, you take out some guys, that gives you another subsequence. The question is, given two sequences, which is that sequence which is the longest common subsequence between these two people? Because once that is there, you can then do the appropriate deletions and insertions. That then tells you how a DNA is related to another DNA. That then leads to war between two groups of people. Okay? So, let us look at the longest common subsequence. So, the standard notation is to take one sequence to be x1, x2, xm. So, this is the input and an input, different lengths. So, you have m and n, and the claim is that this is your output, which is your supposed longest common subsequence between that, and therefore, it has a different substring. Okay? Any questions about the problem itself? Okay, nice. If you look at this, it might look very complicated to you. Meaning that what am I supposed to do? There is stuff happening in the middle. I am taking things out from one side, taking things out from the other side, and trying to find a match. A generative way of doing this thing is to take all subsequences of this, match and see if they are the same subsequence. If they are, note down that this is the one that I found which is the longest so far, and do it overall. That is exponential, you can clearly see. All subsequences of this is essentially setting up a bit string of length m, a 0, 1 bit string. That essentially is going to, when it is 1, it says keep it, when it's 0, it says take it out. So, you are going through all bit strings of length m to power m, you are going through all bit strings of length n to power n, and then you are comparing. I do not care what is happening, this first thing itself is going to kill you. Exponential we do not like. So, the question is there a solution to this problem? A lot of people say dynamic programming. Once again, as I told you, there is nothing called dynamic programming. There is only something called intuitive smarts. You look at this problem, you find a way of solving it, and then you realize that, well, this recursion that I have just made is going to repeatedly solve subproblems, and therefore, let me just store it someplace. That becomes called dynamic programming. So, the way to look at this problem is actually very beautiful. So, you realize all kinds of nonsense can happen in the middle. Yes?
So, if we just look at the problem and solve it, and then we realize that it's dynamic programming, what's the benefit of generalizing them as dynamic programming? I think the benefit of generalizing something as dynamic programming is when we see a problem like this, so we get in our head that that's
Okay, very good point. So, there is a point to dynamic programming, and which is that it is one of those techniques that you keep in your head. So, it reminds you that if you cannot solve a problem in the standard way that you are trying to solve it, try to find a recursive solution to it. However complicated that recursive solution be. Because even if your recursive solution looks very complicated, there is a possibility that you will be able to reduce your its complexity by doing it bottom up. That is a good point. That is why we have dynamic programming. That is why I have been telling you dynamic programming a million times. But after 20 years, dynamic programming will just sit as some little technique in your head. Okay? You will go back to finding recursive solutions. But recursive solutions just do not come just like that. If I give you the recursive solution, you will immediately be able to transfer it into a dynamic program. The question is, can you find a recursive solution? So, what I am trying to tell you is that you cannot tell yourself that I want to solve it using dynamic programming. What you have to tell yourself is that, can I solve this problem using some kind of recursion, for which I need to think very carefully how I will go about solving the problem. Yeah.
What if we take indices in the X and say, I
So the fear, so he's basically saying that what if I start with a small chunk, find the longest common subsequence, let's say, and or some subsequence, let's say, and then try to expand it on the right. The big fear out there is that if you match the wrong things initially, you might not be able to do matches on the right. Now, I cannot tell you that you cannot. Maybe if you think very carefully, you might find a solution to doing that. But if you start in the middle and say, I didn't made something and then I want to match more, it might turn out that if you did this match with this guy, then maybe all these other matches would fit. But because this guy already got matched to somebody else, you're not being able to match it, and therefore you end up with a non-globally maximal solution. But the intuition is right. The intuition is right. Yes.
We can divide x by half and y by half. We have 4 quarters. We can complete it. We can get each quarter subsequence.
Now it will be more complicated. It's another very good idea. You're breaking the two sequences up into 4 pieces, and you're saying, I'm going to match all 4, but then the problem is that if you get a good match between this and that, you're already discarding the left side. Remember, you cannot match in the opposite directions. When the longest common subsequence is happening, the matches have to happen in the same sequence. You cannot say this matches and then the next guy matches somebody on the back, because you have deleted that guy. But all of these are very good ideas. You're already thinking, and you are thinking recursion. You're already thinking, can I take the solution of a small problem and make it a big solution to a big problem? And that's essentially how you should go about thinking about these things. Okay, dynamic programming will come naturally if you know that, okay, if I had the solution for a smaller problem, how can I make it a solution for the bigger problem? That is all recursion is all about, right? It's just flipped over. You say the bigger problem is made out of these subproblems, which essentially means that you say, if I had these solutions, how can I build the bigger solution? It just turns out that all these ideas you have, if you sit for another 15 minutes, you'll realize that you do not want to be playing around with the inside of things. That can mess things up. You want to do it on the corners. That is the only intuition that immediately gives you a solution. Okay? Now, it is not at all necessary that I start with the right corner or the left corner. I can start with the left side. If I give you an algorithm with the left side and you say, no, I have an algorithm for the right side, I would simply say, flip both sequences over and do yours, and you will get my solution. So what I'm going to show you is a solution from the right side, but that does not mean that it has to be the right side. It could be the left side. You can just flip the whole problem and do it from the other side. But the main thing is that you want to do it from that side. Now let me ask you the following thing. If I found out that this is the same as that, they are the same letter, can you tell me something about the longest common subsequence? Yeah, it has to be at least one. Yes, very good. Something else. Something a little more.
If you remove them both, it's going to be the longest sequence when you remove
So immediately you can tell the following. It is not possible for zk not to be this letter. If zk is not this letter, then it means that zk somehow match some people here to some people there, because neither that letter nor that letter is zk, right? And therefore, I could actually add an extra letter called zk, which is the same as these letters. That would be an even longer subsequence. And therefore, the previous one could not have been the longest common subsequence. Yes?
But if you have, if x is y1 to yn, then other letters, then zdk would be yn, xn with yn. Right?
Okay. So you are now confused. Are you saying that I have to match the last two guys if they are, is that what your question is?
No. If we have x values are y1, y2 to yn.
Okay.
The other values.
And more values.
Yes. Then ZK will be yn. And
But not.
not xn with y.
Okay. So now he got it. So essentially what I'm saying is that this letter is the same as these letters. I did not say that you have to match these two guys. If these are the same letters, then this has to be that letter. That is all I'm claiming. The argument was essentially, what if this sequence is essentially this sequence and more, but the last letter is the same as this letter? Then I could have matched it directly inside and left the last guy out. But mind you, the letter is still the correct match, and therefore, instead of matching it with that, I could have as well matched it with the last guy. Would have not made a difference. Do you see that? All I am arguing is that if these two letters are the same, then this has to be that letter, and I can actually match these two guys to be one of the longest common subsequent solutions. If you thought that you can match this letter with somebody else, there is all this space, I can take that out and I can still match it with this. So, if this were the match, I can still make this match. If this were the match, this sequence has ended. So, there is nothing else that is coming out. So, rather than matching it with this, I said delete all of these and match it with that. It would be the same solution, same length, right, and the other way around too. So, essentially the main thing that you see is that if they are the same letter, then this has to be that letter, and you can actually take these two pieces out and say that the main solution is the longest common subsequence for that part plus this letter. I have just turned your bigger solution to the smaller solution plus something. The only other possibility is that these are not the same. If these are not the same, then it gets a little complicated for me. Here is my claim. If these two sequences are not the claim, I tell you that do the longest common subsequence this way. Take this last letter out, do the longest common subsequence, set it aside, then take this out, do the longest common subsequence, set that aside, look at these two solutions, give me the longer one, that is the answer. And it should be relatively obvious to you that there cannot be a third answer which is the longest common subsequence. If the longest common subsequence, if I give you the answer and you know that these are not the same, then you know that Zk is either going to be this or that or somebody else. If it is one of these, it essentially means that if you take that letter out, then you have x without the last letters will still match, because Zk turned out to be this letter, the letter, not the position itself. It turned out to be this letter. So, if I took out, and this is not that letter. So, if I took that out, it would give me the same solution, and likewise the opposite way. So, I have essentially turned my big problem into two cases. One is if they are the same, then solve the longest common subsequence problem for one shorter, and add this letter to it. That will be the longest common subsequence. If they are not the same, solve two longest common subsequence problems, one with this one gone, the other one with this one gone, compare these two and give me the bigger answer. Okay. It is a many if then else based recursion, but you can clearly see I am taking a bigger problem and slightly shrinking the problem. So, in all cases it is actually a valid recursive solution. I have changed the size of one of the sequences to be slightly shorter. So, here is my answer. Exactly what I told you. Cij is just going to give me, in this case, the length of the longest common subsequence. I have, while I am calculating the length, I will also be able to produce for you the sequence itself. It is 0 if either sequence is of length 0. If not, if xi and yj are the same, then it is the longest common subsequence length of one shorter from both sides, I minus 1, j minus 1, plus a 1, yes.
So in the worst case, it will be 2 to the power n.
I will show you that this can be, yes. In the worst case, if you write this recursive solution, it will be 2 to the power n. Now you will apply dynamic programming. But hold on for a moment. And the final one is C I minus 1 j and I j minus 1. So one shot from the one side, one shot from the other side, and the max of those. So this one is this one plus 1, and the other one is the max of the two. If you wrote this as a recursive problem, you would be in great difficulty. As he pointed out, you would have an exponential solution. It turns out that you are actually solving many sub-problems over and over again. So you can clearly see this C I minus 1 j. Okay, if you have two sequences, sometimes both shrink, sometimes one shrinks, sometimes the other shrinks. If you build the solutions up from the small to the large, then you will be able to compare all three pieces over and over again and build it up. That will kill your exponential and make it just quadratic time. You just have to fill up Cij starting from small i's to large j, small i's to large i's for both sequences. And you will see that the smaller ones can produce solutions for the larger ones. Yes, you will feed a matrix. So Cij here means I and j are large, this side is small c. Okay, so this is where 0, 0 is. You start filling in from that side. So you'll have a big matrix, you will set it up to be clear, and you'll fill things up and you will get the solution at the bottom right. Exactly. And because we have run out of time, I have to do this next time before I get into NP hardness. Okay? So finishing and then NP hardness next time.